Scaling up test time compute with latent reasoning is a paper that came out a couple of weeks ago, and it has a really interesting idea for scaling up test time compute. Kind of the go-to method is something like chain of thought, where you basically have the model just kind of talk to itself and output more tokens. But that is expensive because as the sequence length grows, the memory usage grows, well, linearly for inference time. So that is computationally super inefficient. And there's a lot of different methods, but it usually goes back to having to do something with more tokens. This proposes a different idea, and it's mainly that you can use this recurrent module, this recurrent block, to scale up your test time compute rather than just outputting more tokens. So it's very interesting. They have the model output, or they have the model weights here, so you can just go and use it on Hugging Face, and they have the code here and the data. So fantastic. Truly open source right here. Very big fan of that. I'll just get into the model architecture, and then I'll talk about the loss. And then we'll talk about how this is actually used for scaling test time compute. So just go with me for some of the things that may seem a little weird at first, but they end up working in the end. So I ended up drawing this diagram, and basically we want to take this transformer, we want this recurrent module, and we're going to utilize this recurrent module during inference for scaling test time compute. And we can scale the test time compute by using this recurrent module more if we need to, or use it less if we don't need to as much. So the idea is, let's say we have a sequence of tokens, maybe it's like 1 plus 1, and the model needs to respond to this. So the model is going to be like the answer to 1 plus 1 equals. So like these are easy tokens. Like this is easy. This is part of the prompt. But this token right here is probably pretty hard, comparatively speaking. It needs to be 2, I think. No, I'm kidding. Yeah, it needs to be 2. And this is arguably the most difficult token to output compared to the rest. So intuitively, it makes sense that the model should spend more time on this token rather than the rest here. So the idea is it would utilize the recurrent module less for easy tokens and more for the hard and difficult tokens that it's more uncertain about. We just need to make a model with that. So how do they do that? They have they describe it more in text. So I drew it out here, but it's basically a transformer just with 3 different parts. So instead of me talking about these equations here, I'll send it out, these equations here, but I'll just talk through this drawing. So there's 3 parts. They kind of want to do this recurrence in this latent space. That's what that's the idea. And there are 3 parts. There's the encoder, there's the decoder, and there's the recurrent part. So the encoder is essentially the normal encoder you would see, this embedding layer here. So just these are our inputs. N is the sequence length, V is the vocabulary size, and H is our hidden dimension. That's how they define it. So this is just our embedding block here, normal embedding. And then they have these transformer layers. So they have like 1 or 2, depending on what model they utilize here. So they send it through this embedding layer, and they send it through 1 or 2 transformer layers. And this is just preparing this input. The second part is the recurrent module. So this here is just this is what we're going to do every time. This is just our embedding layer. The second part is this recurrent part, and the recurrent part is recurrent. We're going to iterate, or we're going to send the input. So this part here through the recurrent block. The recurrent block is going to give us an output, and we're going to keep on sending this through the recurrent block some number of times. They define how many times that is later, but just we send it through some number of times. So we get this latent output, and what they do is they concatenate it with this noise here. So this here, S0, is sampled from a normal distribution with some variance. The variance isn't 1. They describe later what the variance is, and that has to do with the number of recurrence operations you do. They also scale the weight initializations based off the number of recurrent operations you do to stabilize the recurrence operation itself, so that it doesn't diverge. If you had a normal initialization, it probably wouldn't work, and it would probably diverge because normal initialization is useful for a single forward pass. This does a forward pass multiple times because it's recurrent. So we take this input, we take this state here, we concatenate them together. We concatenate them together here. We then send it through this A matrix, which is just combining these two outputs here into a single hidden state. We send this through some number of transformer layers. So these are, say, 4 different transformer layers. And this is not a normal transformer. It is a normal transformer, but they use both pre-norm and post-norms. And then the output of the, say, fourth transformer layer is normalized. So for all of these transformer layers, the weights are different. But the weights are going to be shared through this recurrent module. So all these weights are different, but we're going to be sending the output through this over and over again. So we take in these two inputs, we get this output, and what we're going to do is we're going to take this output and we are going to concatenate it with the initial representation here. So take this output, concatenate it with this representation here, or with these latents here, these initial latents, and send it through the block again. And then you keep on doing that. So this initial latent embedding is always sent through the transformer as well as the current state. So it has information from what are the initial embeddings and what is the current state I'm optimizing through this recurrent process. It's just they initialize with this noise here, and the reason they do that is, well, you can initialize this in pretty much any way you want. They initialize it with noise because they want to make this model path independent. So they basically want the model to learn the trajectory rather than the actual location, learn the trajectory of this recurrent operation rather than learning the exact, the position doesn't matter. It's the path that matters. So once we have taken our input, we've sent it through our embedding, we have got this latent representation, and we send this latent representation along with this current hidden state through this recurrent block, say some number of times. They call that R. Maybe that's like 32 or 16 times. We take the final output and we throw it through this unembedding layer, which is some number of transformer blocks. That could be like 1 or 2. And then through this unembedding layer. So it's like a normal transformer where you have your embedding layer, you have your transformer blocks, and you have your unembedding layer. It's just instead of having, say, 100 transformer blocks where they're all different weights, you instead have a small amount of transformer blocks that are used over and over and over again. So, I mean, that's the idea. It's not too complicated. And I think I'll show how they optimize this. So here's the diagram they have. I just wanted to show kind of the inner workings a little bit more. But here you can see that you have your input, you have your embedding layer here, which gives you your latent output. This latent output is then concatenated with this sampled normal distribution, and you get your first state. This will output the next state. You concatenate the next state with the latent representation of your input, and you keep on doing that over and over again until you get your final output, which is then sent through the unembedding layer to get your next word prediction. And they also have that here. This is just a little more drawn out. So they note here that the transformer architecture has both pre and post norm here. They mentioned that is for stability. So it doesn't really matter what you use normally at scale, but it matters here because they're using a small number of blocks and for stability. So here's the loss. The loss, this part here, if we just had this and we had this, that would be normal next token prediction loss. They also take the expectation over the random number of iterations. So normally we just take the expectation over the data, and this is just our negative log likelihood for our next token prediction. This is also the expectation over the random number of iterations. So I mentioned we're going to be doing this recurrence, but I never mentioned how many times we're going to be doing it. We are going to be doing it a random number of times, and that does seem weird, but it does work out. It feels like there's a better way to do this, but this is what they do, and it does work. So, yeah, they basically say they choose a log normal Poisson distribution. I don't know if this choice is. It seems like the choice is arbitrary. I don't think they mathematically derived, oh, we need this exact prior for what we sample, but it's nice. Like the distribution is intuitively nice for what you would expect. So for the number of iterations. So R is the number of iterations we're going to be doing for this recurrent module. This is how many times we're going to be sending the embedding back through that recurrent block. And you can see here, this is sampled R, this is density. The majority of the sampled Rs are very low. So intuitively, most tokens in a sequence do not require the same amount of, say, thinking or require the same amount of computation budget because most tokens are not that complicated. However, there do exist some tokens that do require a lot more iterations because these tokens are more complicated. Or rather, the tokens are they're harder to predict than other tokens. So that's what this distribution is saying here. It's saying we know that most tokens take about the same amount of compute, like we would want to allocate the same amount of compute to them, but there do exist tokens that require a lot more compute. And that's just what this distribution is. There's a high mass here, but there is a very large tail for those outlier tokens. And they just take the expectation over that. They also do this truncated backpropagation. So if you do a recurrence, say 32 times, that would be very, very expensive. So what they do is, let me just go back up here to this diagram. If they do this, so they do this recurrence, say 32 times, they basically take the last 8 recurrence operations and backpropagate through that. And the nice part about this embedding here being utilized at every layer is, say we cut it off right here, so this part here isn't being, it doesn't get any gradient flow. This still gets gradient signal. So we're still updating our embedding module, even though we're cutting off the gradient flow. And that's just because computationally, this gradient, this will get massive, the graph you have to store for this. So that's what they mention right here. They say fix k equal to 8 in the experiments. And they mention that this allows them to do a lot more, it allows you to do this tail here. So 150 iterations is a lot. Intuitively, if you had 4 transformer blocks and you did 150 recurrence operations, that's essentially like having, that would be 600 transformer blocks, which is very, very expensive. So if you only backpropagate through the last 8 iterations, that would be 8 times 4. So that would be 32. So, and that's reasonable. 32 transformer blocks is reasonable. 600, probably not, especially because they don't have a ton of compute that they're working with. So that's basically the method. Not too complicated and pretty reasonable. And they basically train this to a pretty significant, a pretty large scale and test it against a bunch of different open source models. So let's take a look at that. They have a bunch of interesting stuff here. For example, like this normalization strategy, they mentioned that the norm doesn't matter that much, but the model for small scale, but the model ended up not utilizing the initial embedding, so the latent embedding, which basically made the model completely garbage because it wasn't learning at all. And they had to do some tricks to get that to work here, and that's why they have this gamma scale in the embedding layer. But yeah, they document a lot of things here. So let me just go through I'll just go through the results one by one. So right now, just assume that there exist, let's just assume that the model goes through, say, 32 recurrence iterations, and we just stick with that. But I'll talk about how they change that later. But for now, just assume that we set the number of recurrences to a fixed amount for every token. But there is going to be a way where you can change that. So if we look at this table here, this is basically, they basically have this 3.5 billion parameter model, and they change the number of recurrences. And we can see as you increase the number of recurrence operations on this model, it does do better. Like you can see here, if you just have 4 iterations, I think their biggest model has 2 transformer blocks for the embedding, 2 transformer blocks for the for the unembedding, and 4 transformer blocks for the recurrent part. So that would be 8 transformer blocks total. 4 recurrences would be, say, 32 transformer blocks. So that's kind of the scale you can think of here. But the number of parameters doesn't increase because we're doing this recurrence operation. So you can see here, as the number of recurrence operations increases, it gets better. The model does better here. So that shows that this recurrence actually does matter, and it does help. And it is, so here, this is 32 recurrence operations. It is better than models. They don't really have any models of the same size. They have, say, Pythia 2.8 billion, but they have 3.5 billion parameters, and it is significantly better than that. But it's not as good as, say, a 7 billion parameter model. Well, it's similar to one of the default 7 billion parameter models, but for a really good 7 billion parameter model, it's still not as competitive. But it's pretty impressive that it can get this good of results on these benchmarks with just doing this recurrence operation and, say, half the parameters. So to me, that's kind of promising that, oh, this recurrence actually does make a difference. They show here again that recurrence does matter. So recurrence at test time, how many recurrence operations do you do, and performance. They show that it does better as you increase the number of recurrence operations. So yeah, that is good. And here again, they show recurrence actually does matter. If you look at just a single recurrent operation, so or no recurrence at all, you just send it through once, or 30 versus 32, it's completely different. The accuracy values here, it's not even close. 34 versus 69, and 34 versus 53. So yeah, overall pretty promising. And they also show that recurrence helps for few shots. So if you have low recurrence, it's fine. But if you increase recurrence, it helps with this few shot learning. So also interesting results. So now we can finally get to how do they actually utilize this test time compute ability that they have. So we just trained it on this random distribution of recurrence operations. But interestingly, there does exist if we were to look at, say, the KL divergence from each iteration of this recurrence operation, we can basically see, does this output of the recurrent operation converge at some point? And if we look at this graph, we can see it does, and there's a distribution of these convergences, or of how the model converges. So for easy tokens, it converges very fast. So the KL divergence between the output of, say, the ith operation and the ith+1 operation, it converges to a low value very slow, or very, very, very quickly. Actually, this one may not be the KL divergences. This is the magnitude difference. They use KL divergence up here. But yeah, the magnitude difference, same idea. So the magnitude difference is it converges to some point very, very quickly. So magnitude difference doesn't change much, and that's how you know it converged. Here, yeah, so for these easy tokens, it converges fast, and for these difficult tokens, it converges a lot slower. And I find that quite interesting, because nothing told the model it needs to converge fast. All we did is we trained it on a distribution of recurrent values, and the model ended up learning this recurrent module that converges quickly for easier tokens and slower for more difficult tokens. But nothing told the model to do that. If it wanted to, it could utilize a ton of recurrence operations for every token. So what this allows you to do is it allows you to do an early stopping. Let's say we define a threshold value. So a threshold value where the iteration value converges to a point, so where the output of the recurrence module doesn't change. If you define that value, you can do this early stopping. So say like right here, it doesn't change that much. Like the value doesn't change that much after you sent it through the recurrence operation, recurrence module some number of times. You can define that as your early stopping. And that allows you to allocate more compute towards more complicated tokens, making like if it doesn't hit this threshold, it'll need to do more iterations until it does. So that allows you to allocate more compute towards more complicated tokens that take more recurrence, that do more recurrence operations versus tokens that don't do a lot of recurrence operations, which is very cool. It allows you to do this test time scaling. So very different from normal test time scaling where you allocate more tokens. But basically, if this recurrence module stops, if this recurrence module converges, you're good. That you can take the output of that token and just do this iteration until it does converge or until it hits some value where you're like, all right, that's enough recurrence operations. Here, they look at the early exits for different types of scenarios. So like high school math, they find that the mode is like it's right skewed and the mass is kind of in the lower values of R. So yeah, this is easier, I guess, versus things like philosophy, logical fallacies, and moral scenarios. It's more left skewed, and you have the large mass in the right side, so it has to think more, I guess, if you want to call it that. But it does more iterations, meaning that the hidden state converges a lot slower for these higher, or for these more logical philosophy scenarios. So I don't know, does that say something about what it's doing? Maybe. So they also mention that you can, they also mentioned this KV cache problem. So for the KV cache, if you have a KV cache, normally you have to do KV caching, but if you do an early stop, then the KV cache that you currently have is like, there's going to be a problem because you don't have that for every recurrent iteration. They mention instead, they just attend to the last deepest available KV state in the cache because all recurrent KV cache entries are generated by the same KV projection matrices from the successive hidden states they match, and therefore the model is able to attend to the latest cache entry from every previous token, even if computed at different recurrent depths. So it's not a problem, but they mention it here just because that's something I kind of thought of like, oh, what about the KV cache for each iteration? They just use the last KV cache and it works fine. They also mention you can do speculative decoding. So speculative decoding, you usually have a small large language model that basically does a bunch of guesses for the next tokens and the larger model that basically evaluates those. And they mention here, you can do that. They say our model can naturally be run with fewer iterations to draft the next token and tokens in the generated sequence, which I cannot speak, which can then be verified with any desired number of iterations is greater than n later. So that's cool. You basically get speculative decoding for free with this by having your draft model be a low number of iterations and having your verification model being a higher number of iterations. I wonder how much better, or I wonder if this works as well as speculative decoding. And if you don't know what speculative decoding is, don't worry about this. But If you do, then yeah, you don't need to train two models for this. You can just use the exact same model, which is fantastic because using two models is not optimal at all. So very nice. You get speculative decoding for free. Is it as good as normal speculative decoding? I don't know. I don't think they have like that, but they mentioned that you can do it. Finally, one thing that I think is really cool that they show is this. They basically do a PCA of, I think it's a PCA of the hidden state of this recurrent operation, and they look at the convergence of it, and they show that some tokens have this faster convergence to a point while others don't, and some others get this weird loop, this weird like it doesn't converge, it goes into this spiral pattern. So yeah, I don't know what that means. They don't go into it that much, but it's interesting. This is kind of more for tricky, like it goes into this this orbit around this point here, and it goes into this orbit for more tricky problems. Like they mention here, this is this answer here for the value 3. It goes into an orbit. So for more tricky problems, it goes into an orbit around some point. I think this would be really interesting to look into more. They only briefly mention it here, but the hidden state or the dynamics of this recurrence module, I think, would be really, really interesting because it's essentially this differential equation that you're solving. So you have this trajectory that this model is moving in, and you can visualize that really easily here. So I think visualizing that more would be really, really cool to see what exactly is going on. But here they show you have fast convergences, you have slower convergences, like this is moving all over the place, and then it goes into a spiral. They also mention that, like before, I mentioned, you need this, you use a normal distribution so that you have path independence. And that's what you kind of see here. Like this path is very similar to this path here. And they do two different initializations. So you do get path independence with this, which is what you want. You don't want the model to care about the exact location. You want it to care about the path that it takes. So that's what they mention here. And yeah, they're looking at the norm distances. So yeah, that's the paper. I think this has path independence. I think this has a lot of I think this is a really interesting paper, and I think it has a lot of directions to kind of scale up and improve and see, does a recurrent method do better than normal methods? Like, does it actually at really, really large scale? Because they were only able to do this at they were able to do it at a reasonable scale, but not at a very large scale that a lot of models are currently at. Like, I don't know how many 400 billion parameters and stuff like that. So I think this is a really cool paper. I think that the method that they have is very interesting. It's very different compared to a lot of other methods where you're just scaling up the number of tokens it generates. And yeah, I think it's a much smarter approach. But I think there could be some areas there's definitely some areas to improve. Like maybe the way you sample R can be different. What does R have to be? Like the number of recurrence operations, what does that have to be instead of doing it randomly during training? Can you find a metric for R while you're training to, I don't know, maybe allow the model to figure out the number of iterations in a better way? Because it's weird to me that it does figure out, it can do less iterations versus more iterations for harder versus easier tokens, or rather it converges slower or faster. So yeah, anyways, enough with me rambling on about this. I think the paper is cool, and I'm curious to see where it goes.